Today we are going to discuss the variation of conductivity and molar conductivity with concentration. First, let us discuss the variation of conductivity with concentration. Conductivity is denoted by kappa. Variation of conductivity with concentration. First, let me define the word conductivity of an ionic solution. Conductivity of a solution at any concentration is the conductance of unit volume of solution kept between two platinum electrodes with unit area of cross section and a distance of unit length. So when we say the word conductivity, conductivity is used to find the conductance of unit volume of solution. Okay, now let us see what happens to conductivity when concentration increases. We know that as concentration of the solution increases, the number of ions per unit volume increases, conductivity increases. So we can say as concentration increases, conductivity increases. Now, what happens when you dilute the solution? On dilution, we can say that the number of ions per unit volume decreases. So, if number of ions decreases, conductivity decreases. So, on dilution means as concentration decreases, or on dilution or as dilution increases, conductivity decreases, because dilution increases means the number of ions per unit volume decreases, conductivity decreases. Now, this variation of conductivity with concentration is same for both strong and weak electrolyte. Next, let us see the variation of molar conductivity, that is lambda m, with concentration. Variation of molar conductivity with concentration. Now, molar conductivity is the conductance of volume V of the solution. So, here we have to consider the total volume V of the solution. And we know that the expression for molar conductivity is lambda m is equal to conductivity kappa by C. And this is the expression when kappa unit is in Siemens meter inverse and molarity is in mole per meter cube. And we know in molar conductivity we consider 1 mole of electrolyte. So suppose V meter cube of solution contain 1 mole of electrolyte, then you know the molarity C, the expression for C, molarity is number of moles divided by volume of solution, number of moles of solute divided by volume of solution in liter. So, here we will have C will be equal to NB is equal to 1, because this V meter cube of solution contain 1 mole of electrolyte. So, number of mole is equal to 1. So, C will be equal to 1 by V. Now, I am going to substitute 1 by V instead of C in this expression. So, lambda m will be equal to kappa into V. Now, when you look at this expression, you can see that as volume increases, molar conductivity increases. Volume increases means as dilution increases, molar conductivity increases. And if concentration increases, molar conductivity decreases. So, what is the variation of lambda m with concentration? As concentration increases, lambda m decreases. But as dilution increases, lambda m increases, because as dilution increases, volume increases, molar conductivity increases. So this is the variation of molar conductivity with concentration. But the variation of molar conductivity with concentration is different for strong and weak electrolyte. So next we are going to discuss how molar conductivity vary with concentration for strong electrolyte and how molar conductivity vary with concentration for weak electrolyte. So next we are going to discuss variation of molar conductivity with concentration for strong electrolytes. How does molar conductivity vary with concentration for strong electrolytes? Molar conductivity for strong electrolytes increases with increase in dilution, that we already discussed. As dilution increases, volume increases, molar conductivity increases. So for strong electrolyte, molar conductivity increases with increase in dilution, but that increase in the value of lambda m is very small. Why? Because you know that strong electrolyte ionize completely in solution. So on dilution, what happens? The number of ions remains constant, but the interionic attraction, that is the force of attraction between the ions, decreases, mobility of ions increases, molar conductivity increases, and it reaches a maximum limiting value at infinite dilution. Now, we have a mathematical expression to study variation of molar conductivity with concentration for strong as well as weak electrolyte. But now we are going to discuss about strong electrolyte. And that mathematical expression is lambda mc is equal to lambda naught m minus a root c, where lambda mc is the molar conductivity at a given concentration. Lambda naught m is called limiting molar conductivity. Limiting molar conductivity or molar conductivity at infinite dilution, or molar conductivity at zero concentration. So this is lambda naught m. Lambda naught m is called limiting molar conductivity or molar conductivity at infinite dilution or molar conductivity at zero concentration. What do you mean by limiting molar conductivity or molar conductivity at infinite dilution? Molar conductivity at infinite dilution means that infinite dilution means the solution is so dilute that even if you add more water, it does not bring about any change in the value of lambda m. So that is infinite dilution, or we can say at infinite dilution the concentration will be zero. So we can call this as molar conductivity at zero concentration. Now A is a constant. A is a constant whose value depends upon the type of electrolyte and the nature of solvent and temperature, and C is our molarity. Okay, so this is the mathematical expression to study variation of molar conductivity with concentration. Lambda m is equal to lambda naught m minus a root c. Now I am going to rewrite this expression. Lambda mc is equal to lambda naught m minus a root c as lambda m is equal to minus a root c plus lambda naught m. Now this equation is of the form y is equal to mx plus c. So I am going to plot a graph between lambda m and root c. So a graph is going to be plotted between lambda m and root C, and this is the graph for a strong electrolyte to study the variation of lambda m with concentration for a strong electrolyte. Now when you plot the graph, we get a straight line, and that is straight line is obtained, and when you extend the graph or extrapolate the graph, it will meet at a limiting value called lambda naught m, and we call this lambda naught m as limiting molar conductivity or molar conductivity at infinite dilution. So how will you define limiting molar conductivity? It is the molar conductivity of a solution when its concentration approaches 0, that is at infinite dilution. Now you can see this is the graph for a strong electrolyte, that is variation of molar conductivity with concentration. As dilution increases, molar conductivity increases, and it reaches a maximum limiting value at infinite dilution, and that maximum limiting value is known as limiting molar conductivity, denoted by lambda naught m. So to get the value of limiting molar conductivity for a strong electrolyte, if we extend or extrapolate the graph, we get the value of lambda naught m, or the y-intercept gives the value of lambda naught m. Now the slope of this graph, slope is equal to minus a, and intercept will give the value of lambda naught m. So this is the graph to study the variation of molar conductivity with concentration for strong electrolyte, and to know the value of limiting molar conductivity, we can extend the graph, and the y-intercept gives the value of lambda naught m. Now let us see the variation of molar conductivity with concentration for weak electrolyte. Variation of lambda m with concentration for weak electrolyte. Now we know that weak electrolytes means they ionize partially in solution. So on dilution, what happens? There will be more ionization, means more number of ions are produced. So we can say for weak electrolyte, the molar conductivity increases with increase in dilution, and that increase is very steep or very high, because more number of ions are produced on dilution. Okay. Now again, if we plot a graph between lambda m and root C, we get a graph like this. This is the increase in molar conductivity, and it increases steeply, and here we cannot get the value of lambda naught m. So lambda naught m of weak electrolyte cannot be obtained graphically, because we cannot extend it to a limiting point. Okay. So how to find the lambda naught m or limiting molar conductivity for a weak electrolyte? That is done with the help of a law called Cauldrous law. So this is the graph for to study the variation of molar conductivity with concentration for a weak electrolyte. Now let us study Cauldrous law. Cauldrous law of independent migration of ions, and this is used to find the limiting molar conductivity for a weak electrolyte. I'll give the statement of Cauldrous law. The law states that limiting molar conductivity of an electrolyte can be represented as the sum of individual contributions of anion and cation of an electrolyte. I'll repeat. It states that the limiting molar conductivity of electrolyte can be represented as the sum of individual contribution of anion and cation of an electrolyte. For example, this law, with the help of this law, we can find the limiting molar conductivity of a weak electrolyte, as well as if you know the molar conductivity of the ions, we can find the limiting molar conductivity of a strong electrolyte also. So, suppose lambda naught Na plus and lambda naught Cl minus represents the limiting molar conductivity of Na plus and Cl minus ions. Then we can say, according to Cauldrous's law, the limiting molar conductivity of sodium chloride will be the sum of limiting molar conductivity of cation and anion. That is, lambda naught NaCl is equal to lambda naught Na plus plus lambda naught Cl minus. So this is Cauldrous's law. Now let us see what are the application of Cauldrous's law. The first application of Cauldrous's law is to find lambda naught M of weak electrolytes. Now we can find the lambda naught M of weak electrolyte if we know the lambda naught M values of strong electrolytes, or from the knowledge of lambda naught M, limiting molar conductivity values of strong electrolytes, we can find the limiting molar conductivity value of a weak electrolyte. Now how is it? Take example of acetic acid, CH3COOH. We know that acetic acid is a weak electrolyte. So acetic acid dissociates into acetate ion and H plus ion. Now to find the molar conductivity, limiting molar conductivity of acetic acid, we have to take two strong electrolytes, and that electrolyte should contain, one should contain acetate ion. So you have to take a strong electrolyte which contain acetate ion and another strong electrolyte which contain H plus ion. So I am going to take CH3COONA. This is a strong electrolyte, sodium acetate. We know that if the acid is weak, its salt will be strong. So sodium acetate, it contains CH3CO minus, and the next electrolyte, strong electrolyte which contains H plus, I am going to take HCl. You know that HCl is a strong electrolyte. So if you know the lambda naught M value of sodium acetate and lambda naught M value of hydrochloric acid, from the you can add this. Now this Na and Cl, sodium chloride, is a strong electrolyte, but we know we have to subtract it to get CH3COOH. So minus lambda naught NaCl will give the value of lambda naught of acetic acid. So if you know the limiting molar conductivity values of strong electrolytes, we can calculate the limiting molar conductivity of a weak electrolyte. So lambda naught of acetic acid is equal to lambda naught of sodium acetate plus lambda naught of HCl minus lambda naught of NaCl. Now the second application of Cauldrous's law is calculation of degree of dissociation. Denoted by alpha. Degree of dissociation denoted by alpha. So if you know the limiting molar conductivity and molar conductivity at a given concentration, we can find the degree of dissociation alpha. So alpha will be equal to lambda MC divided by lambda naught M. So this is the expression to find the degree of dissociation of a weak electrolyte, that is lambda mc by lambda naught m. Lambda mc is the molar conductivity at a given concentration and lambda naught m is the molar conductivity at infinite dilution. And for weak electrolyte, we know that at infinite dilution, that is when concentration approaches 0, the value of alpha will be equal to 1 for weak electrolyte at infinite dilution. Okay, now the next application, number 3. Now, calculation of dissociation constant of weak electrolyte. Dissociation constant, if it is an acid, it is denoted by Ka. So, acid dissociation constant will be equal to C alpha square divided by 1 minus alpha. So, if you know alpha, that is the degree of dissociation, you can find the dissociation constant. Ka is equal to C alpha square divided by 1 minus alpha. So, these are the different applications of Cauldrous law. So, with this we finish the variation of molar conductivity with concentration for strong as well as weak electrolytes. Thank you.